Thank you again for the introduction. And I'm a research scientist in Professor Chuang's lab at RPI, and it is a great pleasure to have this opportunity to present my previous work on multimodal foundation model and large language model. This work is more about the image analysis and text analysis. So the first part is about medical multimodal multitask foundation model for lung cancer screening. So lung cancer is still the leading cause of cancer death, and the well-known national lung screening trial has demonstrated that 3D low-dose CT lung cancer screening can reduce lung cancer mortality by 20% than the 2D chest X-ray imaging. As a result, annual lung cancer screening is recommended for eligible smokers. However, there are various challenges to implement lung cancer screening. For example, the low screening rate, high false positive rate, and underutilization of multimodal data, and particularly a shortage of radiologists for providing lung cancer screening. With the rapid development, AI promises to improve lung cancer screening's quality and efficiency. So currently, the most advanced model is driven by foundation model. And we all know that AI performance increases with scaling up computation data and model sets as demonstrated by the scaling laws. And on the other hand, multimodal modeling can improve the AI performance as demonstrated by GPT-4o. And more importantly, it is desired in the real-world applications such as lung cancer screening. So in this project, we aim to develop a multimodal foundation model for lung cancer screening. However, there are two main challenges. A data challenge, there is a high bar to systematically curate large-scale multimodal multitask data sets in alignment with the real-world lung cancer screening workflow. And the model challenge, there was no scalable foundation model dedicated to lung cancer screening, especially for processing the 3D CT data. Previously, the foundation model mainly processed the small natural images like in ImageNet. However, the 3D CT data is much larger than the natural images, and it's very challenging to build such a foundation model for 3D imaging. So to address the data challenge, here we present a data construction workflow. First, we define a set of tasks of interest in alignment with the real-world lung cancer screening workflow. Then we collect task-specific multimodal data like demographics, disease history, smoking history, imaging data, pathology results, and the radiology reports and follow-up data. And then we pre-process these multimodal data and align them for each specific task. And finally, we build a multimodal question answering data set. In this study, we collected totally over 42,000 patient data, 49 clinical data types, including 160,000 3D CT data, and covering 17 clinical tasks. These data are from National Lung Screening Trial and Matrix dataset. We also independently collected a large-scale data from Wake Forest University School of Medicine and MGH for external evaluation. And based on the public dataset, we also curated pre-training CT pre-training data sets, and then we also simulate the clinical data sets for clinical information retrieval. So this slide shows some details about the MQA data set. It consists of text input, image input, questions, candidate answers, and the label source. So for example, So here for the lung risk prediction task, the text input includes like demographics, smoking history, disease history, personal cancer history, and familial lung cancer history. Then the image input are the 3D CT regions about the lungs. And then here is an example instruction or question that predict the lung cancer risk over 6 years. And then we have the corresponding binary labels over the 6 years. Those labels are calculated from the pathology results, follow-up data, and the death report. So the table on the right shows the full list of the data elements used in this study. So after curating a large-scale data set, we designed a M3FIM architecture. So here is the illustration of input and output. The input here includes 3D CT with organ bounding boxes that's pre-calculated. And then we also input the voxel size because this voxel size is very important in some tasks. And here we also disentangled the voxel size from the image content, which is much consistent with the radiologist's interpretation procedure. And then we input clinical text covering various clinical data types. And then we can ask some questions and or some instructions about the lung cancer, about the lung screening tasks. And then we can get a corresponding answer. That is predefined according to the medical expertise. And then the M3FM can only take the text as input. Here is the text about the lung nodule description, and then the model can automatically calculate lung res score. So here is more details about the architecture. So figure A shows the details about architecture. Here we designed a CT vid to process multi-scale 3D CT scans, and also it can perceive the voxel size. And in figure B and C, we show the pre-training process for CT vid and the text transformer using masked autoencoding. We can learn some representations here, and it will make the training easier for the end-to-end training. So in figure D, we designed a distributed task parallel training. So in different tasks, the M3FM can take different input combinations, and also it can take different sizes of CT images as input. And the different tasks, they may have different loss functions. So this strategy is very flexible to include more clinical tasks and the data size. So the models were trained using 192 GPUs across 32 nodes in the supercomputer in the Center for Computational Innovation at RPI. So also to study the scalability, we trained 3 versions, including base, large, and huge. So this table compares M3FM with all previous AI models related to lung cancer screening. So we can see that the previous models that can process 3D CT data, their model size is much smaller than M3FM because the large input is very challenging. So here we evaluated different models on the curated large-scale evaluation data sets. So we can see that M3FM achieves SOTA performance across all the 17 tasks, and it can improve the lung cancer risk prediction by up to 11% in terms of the AUC metric. And here is the scalability results. Generally, with larger model sets, we can get better performance. Especially from the base to large, there is a big improvement. However, from the large to huge, the improvement is relatively small, and sometimes is even dropped a little bit. We believe this is because the current data set is not large enough for training huge data. Although we already use the largest data sets in this domain, but the data set is much smaller than the data sets used in the general domain. So we further conducted a lot of ablation studies. We showed that the multimodality models outperform single modality models. On the other hand, multitask models surpass single task models. We further gave another analysis that for the 5 tasks that were not benefited from the multitask learning, we found that they have the most balanced data set. That means the multitask learning is more beneficial for the tasks with imbalanced data sets or a smaller number of positive or minority class labels. So this result is very informative because most of clinical tasks have a very imbalanced data set, so they can generally benefit from multitask learning. And then we further evaluated the effects of size embedding. As we mentioned before, we found that voxel size embedding can benefit various tasks. For example, it can improve the lung cancer risk prediction by 5% to 12%. Actually, this result is reasonable because the lung nodule size is the key factor of lung cancer. So then we further visualize the attention maps over multimodal data, including both the 3D images and the textual clinical data. So interestingly, it revealed that the history of heart attack, hypertension, diabetes, and stroke are highly informative for CVD, which is actually common knowledge. And this finding is further confirmed with our statistical results in the table. So actually, this result suggests that M3FM can identify the informational elements in the multimodal data, and also it can provide certain interpretability, how the model makes the final decision. And next, we evaluate the models on the independently collected data sets from MGH and Wake Forest University. And we can see that M3FM significantly boosts the performance on the independent data sets. In particularly, it improves AUC by 20% for 1 year lung cancer risk prediction. And furthermore, in these experiments, the multimodal multitask learning can also benefit the generalizability. So lastly, we evaluate the adaptability of this model. And we fine-tune the pre-trained M3FM on the screening data sets to a new task for the prognosis task. And we can see that M3FM can boost the new task by 5% in terms of the five-fold cross validation. Actually, this result is very promising because especially if for some tasks we cannot collect a lot of data, but we can collect a lot of data related to this task, so we can use the foundation model to boost the AI performance. And in summary, for this work, we present the foundation model for lung cancer screening, and also we curated a large-scale open M3 test data set achieving SOTA performance, and we also demonstrated it's scalable and adaptable. Actually, this is big teamwork among RPI, Wake Forest, and MGH. And our code and data sets are available online. So actually, we are now extending this work to include more clinical tasks in screening, their diagnosis, treatment, and prognosis. So we need a lot of computational resources. Fortunately, this follow-up project was selected as an exemplar project representing RPI to access Ampere AI systems, which was funded by the New York State. Because of this, this project gets like much broader attention than we thought. And last Thursday, News 10 ABC reporter just interviewed our lab and asking about a lot of questions about this project. Actually, this is, I was very excited because this is my first time to get an interview. So a lot of fun there. And the second part is about dynamic template constrained large language model for fully structured radiology reporting. And currently, the radiology reports in lung cancer screening is called level 1 structured layout. That divides the reports into different sections. Following each section is the free text descriptions. However, in the radiology community, the standardized and fully structured report, or called level 2 structured report, is more desired because this fully structured report can fully represented in a table. And it has been demonstrated that the fully structured report is more accurate and more consistent. Apparently, the fully structured report is more actionable. We can easily search, analyze, and compare data in the table. And I think most importantly, the structured report can be used to build very large scale data sets for AI training and especially for evaluation, because we can easily extract many detailed labels. However, the reporting tools now is clunky and time consuming. For example, here, the drop-down menu solution requires many clicks, so it's very time consuming, impossible to be implemented in real world workflow. So here we present an LLM solution that the radiologist just reports as usual using the free text descriptions, and then the LLM will automatically and quickly return the structured reports. However, if we directly use the current large language model for this task, there are several challenges. The first one is the formatting error. So like here, we usually use the JSON format to represent the structured output. If just the single comma is generated here, it will lead to failed conversion. And also, different radiology reports may have different number of lung nodules. So we need the template to be dynamic. And also, the large language model may generate some content hallucination. Like here, the shape is not a type of shape. The smooth is not a type of shape. So also there is some privacy concerns. So to address this problem, we designed a dynamic template constraint decoding. And apart from the user input, we also input a template as a constraint so that there is no formatting error, no content hallucination, and no privacy leakage. The key idea is to divide the output tokens into two categories. One is the formatting tokens. We keep those tokens fixed without prediction, so we can avoid the formatting errors. And also, the second type of tokens is called special value tokens. For each special value tokens, we have corresponding predefined candidate tokens, so that the predicted tokens are strictly from the predefined ones. We can avoid content hallucination. And here we also used a special token to dynamically adjust the template. So here is the template we constructed for lung nodules, and it consists of a rich set of features, and for each feature we predefined standardized terminologies. And here we constructed across institutional data sets so that we can evaluate if the large language model can standardize and convert the free text report to the fully structured report from different institutions. And we implemented the proposed inference methods to various representative open source models. We can see that the proposed method can consistently improve the performance. It can boost the largest llama model with the 400 billion parameters by up to 10%. And then we explored some use cases of the fully structured report converted by the large language model. And previously, if we want to do some statistical analysis, we need to manually extract a lot of detailed information from a lot of historical radiology reports, which is very time consuming and is impossible to build very large data sets. So with the large language model we designed, it can accurately extract those information. And we found that the automatic statistical results are closely consistent with previous findings that obtained using the manual extraction information. And we also built a nodule level retrieval system. So here, for example, here we input solid and increase or new. All the individual nodules can be listed, and also with their corresponding annotated slices. So I think this system has some use cases like education and search some specific cases. So in summary, this work, we presented a dynamic template constrained large language model for structured radiology reporting, and we also explored some use cases. Also, this automatically converted fully structured reports. It can also fully automatically calculate the long rise, and which is much accurate than directly using the large language model. The archive version is available online. Also, we released our software based on the LLM, so we can download just the open source model and use our inference method. And now we are still training more models or smaller models that can be have similar performance with the larger models, and we will release more models in the near future. So these results wouldn't have been possible without the strong support of the interdisciplinary team led by Professor Chuang in collaboration with the CCR director, Chris at RPI, Dr. Carroll at MGH, and Dr. Whitlow at Wake Forest. Okay, thank you. Happy to take questions.
So there are a couple of online questions here. I have the same question, but this is a question from Xiaowei Wu. Nice work. I want to ask, how do you handle missing data, especially for answers and some of the, the text kind of inputs?
Okay, that's a very good question. So yeah, here's some patient data. We don't have the complete required data. So in the training process, we do some like drop out strategy. We randomly drop out some clinical data, and then it will simulate the situation where in the testing stage, we don't have the complete the clinical data. So this strategy is very useful based on our experiments.
A very impressive work. I have two very detailed technical questions. One is that your base huge and large model are corresponding to the size of VIT base, VIT huge, and VIT large.
Yes.
Okay. The second question is that I didn't find the details how you align the text and the image together.
Okay, yeah, just the show as shown in this picture. So different, based on the discussion with radiologists, we know when they do some diagnosis on some diseases, which regions they are looking at. For example, the lung nodule must be within the lung regions. So we just segment those lung regions previously using some segmentation model and using a bounding box to fit that region. And we don't need very accurate segmentation, just some cross like localization. So in this way, we can align the image regions autonomy to the relevant tasks. Like for the heart disease diagnosis, we just segment the heart region, related region. In this case, we can also save the computational resources because other regions, actually, we don't need to encoding or compute them.
So my understanding is that you input are both text and the images, right?
Yeah, the text is basically aligned according to the tasks. For some tasks, maybe we just need, like the CVD, we just need disease history and the images, but sometimes we don't need other clinical data. So we don't usually align the images and the clinical data. We just align them with the specific tasks.
I see. Thank you.
Thank you.
Okay, maybe one more online question. This is from Chinmay Chakraborty. Question is essentially about, can you talk about the ethical clearance and validation process for handling medical data in this work? So I presume you've gone through IRB and this kind of thing. Can you speak to that at all?
Sorry, can you repeat the question? Is about ethical?
So you're handling large data sets of patient data. I think there's a question online about what is the approval process like for handling these large data sets?
Yeah, the data sets consist of two categories. One is public data sets like LST and Metric. We need to apply for those data sets. They will let you sign some agreement between your institutions and the data center. Then they will send us the data. And for the independently collected data set from our collaborators, because Dr. Wang has a long-term collaboration with Wake Forest and MJH, they spent a lot of time to make the agreement work. So yeah, we indeed have a workflow to get the agreement, and we also got the IRB approval. So yeah, a lot of paperwork.
Yeah. Thank you very much. Let's thank the speaker once more.
Thank you.